Light, 2008 Higher 11, question 9. So in this particular question here, the main focus is on refraction. And like in all the older questions, we're going to have to, first of all, mark all of the questions. I'm going to start calling them A, B, C all the way down. Whereas in the newer exams, that's already done for you. So if we zoom into this question, we can see there are really 6 parts to it. The first 2 parts really are looking at some definitions. So what is meant by refraction and state Schnell's law of refraction. So we're going to start there. So refraction is where we have the bending of light as it travels from one medium to another, where each medium has a different refractive index. So we would be getting 3 for saying bending of light, and 3 as it's saying travelling from one medium to another. And they really always want you to say different refractive index. Sometimes they don't penalise you if you don't say that. So B then is state Schnell's law. So Schnell's law states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant, or we can say sine I is directly proportional to sine or, as long as we state what I and or are. So if we forget to say what I and or are, we would lose marks. So in C here we have the eye. We're told the eye consists of a lens system and a retina, which is 2 centimetres from the lens. And the lens system consists of the cornea and a fixed lens, which has a power of 38 per metre, and the variable internal lens just behind the cornea. The maximum power of the eye itself then is 64 per metre. So the first thing we have to calculate here is how near an object can be placed in front of the eye and still be in focus. So if we were to give ourselves an image of that, so in our eye we have a convex lens, so if we're placing our object in front of the eye, then it'll be brought into focus at the retina at the back here, which is where our image is going to be formed. So essentially what we want is how near can we place that object, in other words, what's U going to be, so that it is still in focus on the retina. And we know obviously that the retina is fixed at 2 centimetres behind the lens. So we know for a convex lens that we have 1 over f equals 1 over u plus 1 over v. But we don't know the focal length. Instead we know the power. And the maximum power of the eye is 64 per metre. We know that the power is 1 over f, which can of course be found on page 60 in our maths tables. So if we sub in our values, we have P is equal to 1 over F. Therefore, F must be equal to 1 over P, which is 64, which gives us a value for F in metres to be 0.0156 of a metre. But we normally talk about focal length in terms of centimetres, which would be 1.56 centimetres. So if we then sub that into our lens maker's formula, we have 1 over 1.56 centimetres is equal to 1 over u, which is what we're trying to find, plus 1 over v, where v is 2 centimetres. And it's very important there to make sure you have your metres and your centimetres converted, because you have to have both v and f in the same units. So rearranging there gives us 1 over u equals 1 over 1.56 minus 1 over 2. So that gives us 0.141. 0.25641. So I want u though, so I need to invert that, which is 7.1 centimetres. So in other words, the closest we can get with keeping an object in focus on the back of our retina is 7.1 centimetres in front of the eye. So there was 12 marks going for that. So we had 3 for our formula, 3 for working out what F was, again 3 for subbing correctly into our formula, and 3 for getting U. And of course -1 if we have no units. So the second part of the question then wants us to calculate the maximum power of the internal lens. So of course we're told the lens system consists of the cornea, which is here in the eye, and then this is the internal lens. So the two of them combined have a power of 64 per metre, and the cornea has a power of 38 per metre. So again, if we're looking at page 60 here, 2 lenses in contact is going to be our combination. So in other words, P is equal to P1 plus P2, where the power of the lens is 64 per metre, and then P1 is 38 per metre. So by subbing in, we have 64 equals 38 plus P2. Therefore, P2, the internal lens, must be 64 minus 38, which is 26. And again, that has to be per metre. And there was 3 marks for that. So a nice easy calculation there. Okay, so in D, we're told that light is refracted as it enters the cornea from air. And we can see that here in our diagram. And we want to calculate the refractive index of the cornea. So we can see that if light is entering air and passing into the cornea, that makes that the angle of incidence, 37. And then on entering the cornea, the light bends. It's bending towards the normal, so this is our angle of refraction here. If we go back here to our tables, again, page 60, we can see our refractive index can be found by getting sin I over sin R. So subbing in our values, we have sin I, which is 37 degrees, divided by sin R, which is 27 degrees. And therefore our refractive index is 1.3256. And we had 3 for our formula substituting in correctly and 3 for our answer. So the second part in this question here is looking at us to draw a diagram to show the path of the ray of light as it passes from water of refractive index 1.33 into the cornea. Now, if we look at the refractive index of the cornea, we've just calculated, we can see that it's 1.3256, which really is 1.33. And because it's the same as the refractive index of water, well, if we were to look at going from water into the cornea, well, even if it hits it at an angle, it would actually pass straight through because the refractive index of the water is the same as the cornea. Now, if you were to take it that it was 1.3256, you might say, okay, well, there's a slight difference there between the two refractive index. So if you were to take that into consideration, you would still only have the slightest of bending there in your diagram. So again, if it was hitting it at an angle, we might find that it's going from more dense to less dense, and in which case, if it's going from more dense to less dense, it would bend away from the normal. So we'd only have the slightest bend away from the normal there. So either of those would have gotten you a full 6 marks. Okay, so the last part, F. We have a swimmer cannot see properly when she opens her eyes underwater. So why does the cornea not act as a lens? So as we saw in our diagram there, the reason it's not acting as a lens is because as the light is not going to be refracted at the cornea because they have the same refractive index. So you were getting 3 marks for saying light is not refracted, and then the reason why, because water and the cornea have the same refractive index. So as a result, if the cornea is not acting as a lens, then the maximum power of the eye, well, if we go back to our previous question here, well, the lens system was the cornea and the lens. But if we don't have air in front of the cornea and we just have water, well, the cornea is no longer acting as part of the lens system, which means then we only have the internal lens. And we worked out the maximum power of the internal lens here in part 2, which was 26 per metre. So that would mean here then in this particular question in F, the maximum power of the eye is only the internal lens. And it was 3 marks for that part. So then it says, well, why do objects now appear blurred when we are underwater? Well, again, if we go back to our diagram of the eye, well, with the cornea and the lens, the closest we could get to our object distance was, I think, what should we say, it was 7.1 centimetres. And then that allows the cornea and the lens to bring the light into focus on the back of the retina. But of course, if the cornea is not going to act as part of a lens system, well, what's going to happen is that that light is now going to go straight through the cornea and only be refracted by the internal lens, which means then that the light isn't going to be brought into focus on the retina, but instead it will be brought into focus somewhere behind the retina. So that means that the lens basically isn't going to be powerful enough to focus the light on the retina. So we were getting 3 marks for stating that the light is not the lens is not powerful enough to focus the light on the retina. And the last part of the question then says, well, explain how wearing goggles allows you to see the objects clearly. So obviously if we have goggles on, what's going to make a difference is that there's going to now be light passing through water and then passing through the lens part of the goggles, but then of course there's air. So the fact that there's air in front of the cornea now means that the cornea is going to suddenly become a refraction, part of the refractive system of the eye again, because we have a different refractive index between air and the cornea. So we were getting 3 marks for saying that light is refracted, passing from air to the cornea. In other words, the cornea is now acting as part of the lens. So a nice little question there, really putting your understanding of refraction and refractive index to work. So 56 marks in total